Thank you very much. Well, good morning, good afternoon, or good night to everybody, depending on where you are. I want to thank especially the organizers for the opportunity, both for the opportunity of presenting this work here, as well as for the courage to, carry on with organizing this fine meeting under these trying circumstances. So, what I'm going to talk about today is a special contribution to the so-called Bartnik conjecture, and I'll talk about that in a moment. But this is joint work with José Luis Flores from the University of Malaga and Jonathan Herrera from the University of Cordoba, and has been published last year in Mediterranean Journal of Mathematics, and where you can look up for further details that I have to omit here. So, okay, this is the general outline. I'll start by explaining what the Bartniks conjecture is and try to motivate why it is important. And then what I'm gonna try and do is to bring a kind of symmetry described by conformal killing vector fields and see how those facilitate obtaining results about the said conjecture. Now, the first question, of course, is what is the Bartniks splitting conjecture? Bartnik, in his PhD thesis in around 88, considered globally hyperbolic spacetimes with compact Cauchy hypersurfaces of any dimension. And at that point, he was interested in certain cosmological models appearing in general relativity. And in particular, he imposed some, the so-called energy conditions, which I'll not have to, not have time to go into. But what these boil down to geometrically is that you have this time-like convergence condition, which I'll just abbreviate by TCC in this talk. And it just states that the Ricci along time-like directions is non-negative. This has physical motivation. And he wanted to see what would happen if he imposed a geodesic completeness along time-like directions for these spacetimes. So he came up with the conjecture. He could not really prove it, but he gave certain sufficient conditions which established this, that the spacetime in that case will split isometrically as a product of this sort, where the spatial part here is just a compact remaining manifold. And of course, this is diffeomorphic with the compact Cauchy hypersurfaces of the original globally hyperbolic spacetime. Now, I want to call your attention to two aspects here. First of all, if you do have the splitting, this conjecture, by the way, is open even today after much effort by many researchers, especially Galloway and collaborators. But this is not quite settled. We came close, but in the last minute, we always have to impose some extra conditions. But I should say that you can see that if the isometric splitting occurs, then you have a killing vector field, ddt here, because of this special form, static form of the metric. The second point I want to emphasize is that if this does not occur in the present, if the conjecture is true, but this does not occur in the presence of the other assumptions here, then you have a time-like geodesic incompleteness. So this can be stated in the form of geodesic incompleteness, or that you have such a splitting, which just gives a special structure for spacetime. This has been stated for any dimension. It has been established very quickly for n equals 2 in an old paper by Ehrlich and Galloway in the 90s, but it, as I said, remains open for higher dimensions. Why should one care? Well, first of all, I should say that this is motivated by general relativity. As I said, Bartnik was interested in cosmological models, and he was actually studying this. There is a well-known description of singularities in cosmological models and black holes via geodesic incompleteness along causal directions. So in geometric terms, what this boils down to is to give physically motivated conditions to establish the existence of at least one causal, either time-like or null, geodesic in your manifold. So one would expect on physical grounds that this phenomenon of the appearance of singularities in this sense would be quite generic, but on geometric terms, what this means is that you should have some sort of specialness in one way whenever you have, under this physically motivated circumstances, geodesic completeness along causal directions. And so the Bartnik conjecture underscores a general philosophy that these geodesically complete manifolds should be very special. I will refer to cosmological spacetimes as globally hyperbolic spacetimes of dimension greater than or equal to 3 with compact Cauchy hypersurfaces and satisfying the time-like convergence condition, but not necessarily time-like geodesically complete. The grandfather of all this conversation is the well-known singularity theorem by Hawking and Penrose in the 70s for this kind of space-time. If you have a cosmological space-time in the sense that I had just described, plus the so-called generic condition, which is a curvature condition, it says that just the so-called tidal force operator along at least one causal geodesic, at least one point of along each causal geodesic, but at least at one point that this curvature object here is non-vanishing. If I remove this, then one can, they actually established that in the presence of this condition, you do have incompleteness, either along time-like or no geodesic directions. But one might ask whether, if I remove this condition, whether this remains true. The answer, of course, is no, but then I might try and say something more about the kind of space-time that you have in the absence of this condition. Let me mention that the original theorem, the condition is not quite as strong as I just stated. It's just necessary that it's chronological and contains a trapped set, but I will not be discussing causality here, so just to stick to original conjecture. I should also say that the generic condition in itself is in a way generic. There are many indications of this, going back to an old paper by Beam and Harris, and also more recently a discussion by Larson, but I will not go into this here. And again, I will refer to these references for further details. The Bartnik conjecture is a rigid statement without generic condition, and I should say that it's false if I drop the TCC, so it's important that I have a curvature condition, otherwise the Sitter space-time is a counterexample. Our results actually are based on a recent result by Galloway and Vega, are motivated by that result, because it's a matter of no little surprise that even if you have a Ricci flat manifold, that is to say, if the Ricci flat just vanishes identically, and if you have a conformal killing vector field, meaning a vector field for which there is a function on the manifold satisfying this equation here, then Vega and Galloway have proved that this actually splits as in the Bartnik conjecture. Now, this case had been open, even this simple case here had been open up to 2017. So we felt like investigating this condition further, because this is interesting for other reasons, and we wanted to understand what kind of role this might play in the original conjecture. So in our paper, what we did was to consider the original conjecture, not necessarily a vacuum, but satisfying TCC, but in the presence of such a conformal killing vector field. What could you say in this case? Well, it turns out that if you carry out a careful analysis, then there are two markedly different situations. One is in which X is a complete killing vector, conformal killing vector field, or the case where it is incomplete. So first of all, we consider the case when it is complete. Okay, let me remove this for the minute, otherwise I will be distracted, but I'll return to that in a moment, okay? And so if I have a global hyperbolic space-time, we'll come back to Cauchy hypersurfaces, and I suppose that there is a complete conformal killing vector field in this sense, then you can show that the so-called non-observer horizon condition holds in the space-time. I will not have time to describe this in detail, but what this amounts to is that you can actually show that there is no line in this, that is to say, no globally conformal, no globally achronal, null geodesic angular space-time. But then you can prove that in this case, you do have what is called a time-like line, that is to say, a geodesic which is globally maximizing, a time-like geodesic which is globally maximizing, and you then can use the so-called splitting Lorentzian theorem in order to establish the splitting in the Bartnik conjecture. So we show that this is the case if you do have a complete conformal killing vector field. This result, as I stated, does not use the TCC. Okay, but some other aspects of this around this, as applied to Bartnik conjecture, does. All right. The outline of the proof is as follows. I started with a complete time-like conformal killing vector. What I do is we rescale the metric like so, where beta is the norm of your conformal killing vector field. Now, it turns out that if you consider now the space-time with this conformally rescaled metric, it is a standard stationary space-time in which X is now a killing vector field. And the compactness of the Cauchy hypersurface now ensures that you do not have null geodesics. This is a well-known result for people who have studied stationary space-time, so there is no novelty here. But null pre-geodesics are conformally invariant. So that means that in the original space-time, you do not have null lines, and therefore you can again construct the time-like lines and prove the splitting via the Lorentzian splitting theory. So this is the general outline. What is also important in this proof is that if you analyze this same scaling, in the case when the X is not complete, then you can show that you can conformally embed your original space-time as a pre-compact region in this standard stationary space-time. That is to say, instead of having a standard stationary space-time like this, what you can do in the case of when you have an incomplete field is to rather embed your original space-time in such a standard stationary space-time as a pre-compact region. This will have importance later, as I will discuss. Our main theorem shows that the presence of a conformal vector field, as I said, we have two markedly different situations, one in which the conformal killing vector field is complete. We have just discussed that case. Now I turn to the case when it is incomplete. Okay, so I have the situation of the original conjecture. In particular, in this case, I do have the TCC. Okay, so I have a cosmological space-time, which is time-like geodesically complete for the purposes of the conjecture. In this case, I have to use the TCC. And my vector field here, as I said, will be assumed to be incomplete. As I said, in this case, we can rescale using the norm of the Killing vector field. I can rescale the metric and conformally embed my space-time in larger stationary space-time, for which X is actually a Killing vector field. And in this larger space-time, my original space-time becomes pre-compact. So it's not quite true that in the incomplete case, I do have the splitting, but I will have the splitting if I impose some conditions on the sigma scalar function that appears in the conformal Killing equation, which is, again, repeated here. If I impose some condition on this function, then I do get the splitting. It seems to be the case that this is always needed. That is to say, at the last moment, you see that whatever you expected to obtain in trying to solve the conjecture, in trying to establish a conjecture, you always end up needing something else that you did not expect at first. And this happens here as well. But we still can give very definite conditions on this conformal, on this the sigma, which is related to the conformal structure. So if I give this condition here, which is technical in nature, that is to say, suppose that I have a future complete time-like geodesic in which this quantity here is bounded. We're going to see why this particular quantity shows up in this context. Then you do have the splitting. Or you can just assume the sigma is bounded. In this case, you also do have the splitting. In order to understand why this is true, I give you a quick outline of the proof. A key ingredient is this well-known formula for how the Ricci tensor changes when you perform a conformal rescaling. Remember that the conformal rescaling here is the hatted metric means beta to the -2 times g, that is the g hat. And then I have this relation for the Ricci tensor in terms of the Hessian metric, in terms of the beta function, and here you have it. This is a well-known formula, and I can calculate with that along the geodesic that I imagine will exist. This case here will be included in this discussion, so I'll just stick to the condition 1 for simplicity. So I imagine and fix once and for all such a future complete geodesic in order to study it. What I do is to consider the Ricci tensor evaluated along this geodesic. But first, I will reparameterize the geodesic by arc length with respect to the hatted metric. Remember that in the incomplete case, my original space-time can be viewed as a precompact region inside a larger stationary space-time. So actually, my original space-time can be viewed as this precompact region, and this is a geodesic in your regional space-time. It becomes now a reparameterized curve, which is still time-like, although it's no longer a geodesic. It's just a pre-geodesic, but it's still time-like. So it cannot stay because the larger space-time is still globally hyperbolic. In particular, it is strongly causal. This cannot stay in this compact region. It has to go out. So we have to reach the boundary. And what I'm going to do is to study what happens with these quantities here when that happens. And I will rearrange this in a suitable fashion. We'll introduce this quantity here, x divided by beta, and then I will end up with this equation here for the relationship between the Riccis. Now, because I have a precompact region, I can show that these two quantities here, the hatted, this hatted quantity here, and this part here should be S hat, sorry for that. These are bounded because of precompactness, because these relate to the extended metric, and inside the extended spacetime, the original spacetime is, as I said, a precompact region. It is not quite clear that this should be the case here, because although the curve will be extendable to the environment, it shouldn't be just C0 extendable, not necessarily C1 extendable. So we have to work a little harder here in order to show that this is indeed bounded. So this is technically a possible technical glitch here, but we have solved it. So what we do is to consider this term here, it is bounded. This term here is also bounded. This term here comes with a minus sign. And if I analyze this term, I see this, what is here in the sandwich with the metric has to be space-like, because U is a unit, G unit time-like field, and therefore it is orthogonal to U, and therefore it is space-like. So this should be non-negative, but it comes with a minus sign, so it contributes with a minus sign. Finally, I have here the quantity that we need to be bounded, and then it shows up here very clearly. So you see that this will have to be bounded. We'll see why in a moment, because I can analyze what happens with this quantity here when I approach the boundary of my conformally embedded spacetime, the larger hatted spacetime, and it turns out that this here explodes, but it comes with a minus sign. Explodes becomes it's not bounded above. I cannot go into all the details, but it turns out that when you analyze the original geodesic, it's actually, as I said, it will be defined over a finite interval. I can study its second derivative. It's as I said, it's C0 extendable, so this has to be dealt with care, but you can do it and show that this cannot be bounded above. So what you had here is something which is bounded, something which contributes with a minus sign, something which I will assume is bounded, and then all you have is that this will diverge to plus infinity, but it comes with a minus sign. So this quantity here, we go to minus infinity. However, this is a violation with TCC, because here on the left-hand side you have the Ricci tensor. Remember that I have to assume the TCC. So in this case, it will go to minus infinity, and this is a contradiction. So I'll have to have the splitting. Okay, so the contradiction here, I should say, of course, is that I have assumed that as my conformal Killing vector field is incomplete, because I have made no assumption about completeness in this particular theorem. So what I do here is either it is complete or it is incomplete. If it is complete, then I have the splitting already. I just wanted to analyze the incomplete case. But when I add this condition here, I find the stated contradiction. So this contradiction actually is with the assumption of incompleteness for the conformal Killing vector field. So as final remarks, we have investigated the geometric consequences for the Bartnik condition in the presence of a conformal time-like symmetry. As I said, all approaches seem to stumble in different guises on the need for geometric control that's not natural from the conjecture parameters. So fresh new ideas are badly needed. So thank you very much.